Hello everyone and welcome to our calculus notes for section 3.3. Today we're talking about increasing and decreasing functions and the first derivative test. So first let's take a look at increasing and decreasing functions. So we know that if a function is increasing, it graphically is going up from left to right. Algebraically we can see here that these y values are getting higher as the x values are getting higher, and that makes our function increasing. Alright, we also know that we can have a function that is constant. So this is just a straight horizontal line here. Graphically, we do get that horizontal line. Algebraically, we say as x increases here, y stays the same. And that is why we call this a constant function. And our last one is decreasing. Okay, graphically, we can see that this function goes down as x moves from left to right. Algebraically, we say as x increases, now your y values are decreasing. And so we call this a decreasing function. Okay, so graphically, easy to see, increasing, constant, decreasing. Algebraically, I think we can understand that as well. What we're going to talk about today is how the derivative is being affected during an increasing, constant, and decreasing function. And right here it says if f prime of x is greater than 0 for all the x in a certain interval, then f is increasing on that interval. So here, from a to b, we would say f prime of x is greater than 0. And that's how we know this is increasing. If f prime of x equals 0, then we know the function is constant. So here, we're going to say f prime of x equals 0. And then if f prime of x is less than 0, then we're going to say this is a decreasing function. So if f prime of x is less than 0, now we have a decreasing function on the interval. Now we can also think about something greater than 0 is positive, this equals 0, and then something less than 0 is negative. Okay, so this is our test to determine where a function is increasing or decreasing. So some guidelines for finding these intervals where the function is increasing and decreasing. And we're going to assume that f is continuous on the interval. It says locate the critical numbers of f on a and b, and use these numbers to determine our testing intervals. Okay, then we need to determine the sign of the derivative f prime of x at one test value in each of these intervals. And then use the derivative test for increasing and decreasing functions. So we're going to test whether it's positive, negative, or 0. So your question is going to say find the open intervals on which the functions are increasing or decreasing. So the first thing we have to do is find the derivative of our function, because we're going to be looking for the critical numbers. So we find our derivative, and this one is 3x squared minus 3x. Okay. After we find the derivative, we have to set this equal to 0 and solve. Okay, so we can factor this out. We would get 3 times x minus 1. And so here, x equals 0 or 1. And these are our critical numbers. Okay, so that was step number 1. It said locate the critical numbers. And now we want to use these numbers to determine our test intervals. So basically, we're going to put our critical numbers right here, 0 and 1. And we're going to be looking at intervals around these critical numbers. So basically, to the left of this, we're going to be looking from negative infinity all the way up to 0. Here we're going to be between 0 and 1, and here from 1 to infinity. Okay, so now we have our testing intervals, and it says determine the sign of f prime of x at one test value in each of the intervals. Okay, so we need to test some values here in each of these intervals. So here we can try something that's just less than 0, so like -1. And so what we're going to do is actually find f prime of -1. Here we could try f prime, something between 0 and 1. Let's just try 0.5. And here we need something greater than 1, so let's try 2, and let's find f prime of 2. Okay. Now you can just type these into your calculator, and you could write your values here. So f prime of -1, that is 6. F prime of 0.5, that's -0.75. And f prime of 2 is 6. Now we don't really care what the values are other than the sign of the values. So basically, is it positive or is it negative? In this case, it is positive. Here it's negative, and here it's positive. Okay, so what that means is, let's do our conclusion. On this interval right here, our derivative is positive. Therefore, we say this is an increasing on this interval. And the interval is -infinity to 0, and that is an open interval. Here, the derivative is negative between 0 and 1, and so we say this is a decreasing function on the interval 0 to 1. And here our derivative is positive, so again this is going to be increasing, and that's our interval from 1 to infinity. Okay, so graphically what we can know here is that at 0 we have a critical number, and then at 1 we have a critical number. And we can find our f values here at 0. So f of 0 equals, that's got to be 0. And then f of 1, that's going to equal, let's see, 1 cubed minus 3 halves. So that's going to be -1/2. And we could plot those points. So we have 0, 0, and 1, -1/2. Now we know our function is increasing, so it's got to be increasing on this interval here. Okay, and then it's decreasing on this interval, and then increasing on this interval right here. Okay, so increasing, decreasing, and increasing. We have something called a monotonic function, which I just want to define for you. And monotonic means that it's either increasing or decreasing over the entire interval. Okay, so something like x cubed is increasing here. Then as it gets to 0, it kind of slows down, but then it keeps on going here. Okay, so you can see it's increasing on this interval and it's increasing on this interval. So this one right here is monotonic. Now if we look at this graph right here, it's -x² when x is less than 0. Okay, -x² looks something like this, so this is increasing. In the interval between 0 and 1, so from here to here, our function equals 0. So right there, it's constant, and our derivative would be 0. And then x minus 1² when x is greater than 1, it just looks like this. And so that's positive also. Now you can see we have positive and positive here, but because of this interval where the function is constant, we would say this is not monotonic. Let's move on. So here is the actual first derivative test. It says let c be a critical number of a function that is continuous on an open interval containing c. The first derivative test states that if f is differentiable on the interval, except maybe at c, okay, so that kind of sets up our thing. We have critical numbers, it's continuous and differentiable. We're going to say if f prime of x changes from negative to positive at c, then f has a relative minimum at c, f of c. So let's think about what that means. Okay, so we're going to have a critical number here at c, and the derivative is going to change from negative to positive. Okay, so on this side, we know that f prime of x is going to be less than 0, and on this side, f prime of x is going to be greater than 0. Now, what do we know f prime of x is at c? Well, we would know f prime of x equals 0 right here. So if we were to graph this, we know this is a decreasing function here. So we know this function is decreasing until we get to c, where it's 0, and then we would know it's increasing afterwards. Okay, so f prime of x is greater than 0, or less than 0, means this is negative and decreasing. And here, on this side, it's positive. So what does that tell us about this point, f of c? Well, we know that c, f of c, is a minimum. Okay, so it's negative to positive, we get a minimum. Now, if f of x changes from positive to negative at c, then we have a maximum. So here, f prime of x is greater than 0, and then at c it switches over to f prime of x is less than 0. So that means we have an increasing function. It hits c and it's 0, and then we have a decreasing function. Okay, so this would be positive, negative. Here's our critical number, and that would make this a maximum. Now, if f prime of x is positive on both sides of c, or negative on both sides of c, then f of c is neither a relative minimum nor a relative maximum. So let's draw both of these situations here. So here's a c, and let's just say f prime of x is positive, and here on this side of c, f prime of x is also positive. So let's think about what that means. It means we have an increasing function, and then at c it's going to equal 0, and then it has to be increasing again. So here we had a positive, here's our critical number, cf of c, but then it's positive again. So notice this is not a maximum or a minimum. The same thing happens if at c the derivative is negative and then is negative on the other side of c as well. So here we have a decreasing function. We hit 0 at c, and then it's decreasing again. So here the derivative is negative. Here's our critical number, cf of c, and here it's negative again. And here we don't get mins or maxes. Okay, so let's go ahead and find the relative extrema of this function, and we are going to use our first derivative test. So the first thing we have to do is find those critical numbers. Okay, and what rule do we use right here? That's got to be the chain rule. Okay, and let's simplify this. Okay, so now we need to find where this equals 0 and where this does not exist. So remember, it's going to be 0 where the numerator equals 0, okay, which is at x equals 0. And then it's also going to not exist, so the derivative is not going to exist when the denominator equals 0. And that's going to happen where x squared minus 4 equals 0. And so here you can see x is going to equal 2 or negative 2. So in this case, these are the critical numbers. So we're going to put those at the points of our intervals, here, here, and here. So we have negative 2, 0, and 2. And our intervals are going to happen in between this. So this is on the entire real number line. So the interval goes infinity up to negative 2, from negative 2 to 0, from 0 to 2, and then from 2 to infinity. Test values, I'm just going to pick negative 3. Here, I'll probably pick negative 1. Here, probably pick 1. And here I'll pick 3. Okay, and again, all we're caring about is the sign. So you can type these into your calculator, and this is about negative 2.3. This one's 0.92. This one here is negative 0.9. And then here, this one's about 2.3. So again, the sign is really what we're looking for. So that one's negative. Here it's positive. Here it's negative. And here it's positive. So that means it's decreasing on this interval, increasing, decreasing, and increasing. And I always just like to draw the picture. So decreasing to increasing, increasing to decreasing, and decreasing to increasing. So this is our min, this is a max, and this is a min right here. Okay, now we just have to do a little bit of work substituting these values back in. So we're going to have a minimum at negative 2 f of negative 2. Negative 2 squared is 4, minus 4 is 0. So this is really at negative 2, 0. We know we're going to have our maximum at 0, f of 0. Okay, so if we plug 0 in here, we get negative 4 to the 2/3, and that comes out to be 2.5. Then we know we have another minimum at 2. Okay, and that's going to be 2 squared minus 4. That's 0 again, so 2 comma 0. We get another minimum. Okay, so let's plot these points. Negative 2, 0, 0, 2.5, and 2, 0. And so we know our function here is decreasing. Here we know it's increasing. We've got a maximum. It's decreasing. We've got our minimum. And then it's increasing just like so. Okay, so we've got our mins and our max right here. All right, let's move on. This next example on your own, so go ahead and find your critical numbers and then use the first derivative test to find the relative extrema. Come on back when you're done and check your work. All right, so go ahead and check your work here, and when you're done, bring any questions you have with you to class.